Okay, let's introduce complex numbers in a little less of a full-on way than we did before. So if you look in the top left-hand corner, they're kind of the things that I'm going to cover. But what we looked at last time was the existence of an imaginary type of number, and that's stemming from just looking at quadratics and stuff and noticing that we can still find the sum and the roots of something that doesn't exist. So we kind of expanded our number system completely and just added something. And we added a number that's in two forms. It's in a form that's got two components. And we said that a complex number looks like Z, and that's just a number, and it's got a real and imaginary part. And the real part was just a number, and the imaginary part was also just a number with an I attached to it. And it was the sum of those two things. And that formed our complex number. So today we're going to dive into a little bit more of what a complex number is and what we can do with them. So most of our discussion last lesson was looking at what we can do with just I, like terms of I, just like all of this stuff is just the imaginary part of our complex number. We haven't actually dived into what we can do with complex numbers. So we've done all the operations like plus, minus, times, and divide, but we haven't done that with complex numbers yet. So we're going to jump into doing that. We've shown how to graph it, but yeah. So you might think of last lesson how we just like kind of introduced a new type of number as a bit of a drastic measure, but in fact that sort of thing's happened a lot in mathematics, obviously not recently, but complex numbers weren't recent either. So complex numbers were made a long time ago, and complex numbers are used in a lot of IT situations and yeah, like in programming and stuff like that, which is a very recent thing. So it's kind of interesting that complex numbers is used in such a modern way when it was developed so long ago. Okay, so I guess you think about the most basic of equations, or not even an equation really, just like 1 plus 2, I guess. That's equal to x, that's an equation, right? Or, you know, I could just write that as 2 equals x minus 1. Well, that only really requires natural numbers, right? So that only requires the natural numbers, so the counting numbers, which are 1, 2, 3, 4, 5. Now, an equation like, I don't know, 5 plus x equals 4, I can't use the natural numbers to solve something like that. So this implies a necessity of integers. So this requires integers. So it was equations like this where they were like, okay, well, we kind of need to come up with the negative numbers, otherwise what on earth are we going to do? Similarly, if I just had I don't know, like 5 minus 5, like what does that equal? If I don't have the integers, then that doesn't equal anything that's in existence. We would have said there's an imaginary answer to that. But then we increased our number system to involve integers, and integers were, you know, -2 to -1, 0, 1, 2, everything that was like a whole number, positive, negative, or 0. And then we saw, well, not we, I keep saying we, but like mathematicians would have seen equations of this kind of form. That's an x, by the way. Equals 4, and they would have been like, hang on a minute, how on earth do I solve that? I can't fit an integer into here, can I? So that required the development of, so this requires the rational numbers or fractions. So the rationals, okay, and same thing. If I had something like x squared equals, am I going to do 2? Yeah, I'll do 2. Something like that. I can't write that, or I can't fit a rational number into here. So then this required irrational numbers. You can kind of see where I'm going with this. Once I exhaust all these options, you can see that like things like e and pi and stuff like that. And then I've got the old x squared equals -1. What does this require? Well, that requires complex numbers. What am I right? Complex C. Okay, so that's kind of where we're at. It just so happens that complex numbers we only learned about in Extension 2, but if you end up studying maths in uni, I guarantee that'll be in one of your first maths courses. I certainly learned about it in the first year that I was at uni. Okay, so we had a look at this in terms of like the quadratic formula and stuff, but there's easier ways to look at it. If I just go, okay, x squared plus 1 equals 0. We said before that I squared was equal to -1, right? So I could replace this plus 1 with a negative I squared. Okay, and if this was anything else, I could use a difference of two squares because these two things are squared and there's a difference. So I could use a difference of two squares to be like x plus I, x minus I, and so therefore x equals plus or minus I. That's one way of looking at this one. So I guess just the knowledge that I can factorize things using imaginary numbers and using our conventional methods of factorizing, so like difference of two squares and stuff like that, in complex numbers. So it's good to know that all the things that we've been learning about still, complex numbers still abides by the rules of algebra, I guess. Okay, so then if I looked at a different example, so minus 4x plus 13 equals 0. Okay, it's really easy to just go into the quadratic formula here. I can tell you right now this thing doesn't have any x-intercepts, so therefore my solutions are going to be complex. But yeah, you can use a quadratic formula here, but there's a different way of doing it. If you're looking at not using the quadratic formula, one thing you could do is try and complete the square. So, you know, I always go like this. I halve it, square it, so positive 4, and then add it on. So x squared minus 4x plus 4 plus 13 minus 4 equals 0. So I've just added this 4 and take away this 4. So this thing factorizes nicely to that. That's plus 9 equals 0. So then x minus 2 squared equals minus 9. X minus 2 equals plus or minus the square root of minus 9. X equals, now this thing on the right is plus or minus 3i. So I'll take the extra step. Minus 1 plus 2, which is plus or minus 3i plus 2. So that means x is equal to 2 plus 3i and 2 minus 3i. Okay, and yeah, that's kind of it. I can obviously write it like this, but I can also write it like this. And it's generally the case that you put the real before the imaginary. So in this case, if I were just to rewrite it, I'd write it as 2 plus or minus 3i. Okay, and so now this thing has complex solutions or roots or x-intercepts or can't think of another word, but yeah. Okay, so that's now in the form of a complex number, and instead of using, I've said this before, but instead of using x, we generally just say z, but considering I wrote this question in terms of x, I'm not going to go ahead and change what the pronumeral is because that doesn't really matter. Okay, so what we're going to look at now is a couple of properties of our complex numbers rather than just looking at the properties of the imaginary parts, which is kind of what we did last lesson. Okay, so if I have two complex numbers, so I'm going to call this Z1, A plus BI, and I have Z2, we'll call this C plus DI. Okay, Z1 is equal to Z2, so two's complex numbers are exactly the same if and only if, so if and only if A and C are the same and B and D are the same. Okay, so all that means is if these two numbers are the same and these two numbers are the same, then the two complex numbers are the same. That's all that means, which should be pretty straightforward. If these were 2's and these were 3's, then obviously these two things are the same. That's all that means. So that's when we have equality within our complex numbers. Okay, so now we're going to look at the real and imaginary part. So I touched on this a bit last lesson, but our real part and our imaginary part. So given a complex number, we'll call this A plus BI. Okay, our real part of Z is the A, and the imaginary part is B. So that's the real part, that's the imaginary part. Some people just get a little bit confused because they'll call the imaginary part BI. That's not true. The imaginary part of Z is just the constant or the number next to the I, the scalar or whatever. That's all I wanted to say about that. Yeah, and I guess you could write, so this thing, you could rewrite that as the real part plus the imaginary part I. If that kind of makes sense, because A is the real part and B is the imaginary part. You just leave the I's on there. So that's, I guess, one way of talking about it. So now I've got a bit of an example. So if I was like, let's call this 1. Okay, given, let's come up with a complex number. What have I got? 3 minus I. That's a complex number. That's fine. It's got a real and imaginary part. Given that, let's evaluate. I want the real part of, we're going to go with z squared minus iz. Okay. So let's just look at this. I've got a complex number. Oops, got a complex number. I'm evaluating the real part of, and then this is kind of our operations that we're going to perform. So z squared minus iz, that's just equal to, now since z is all this, I'm just going to replace these two with this. So that's going to be 3 minus I squared minus I times 3 minus I. I hope that makes sense. It's just another way of doing an algebraic substitution, but yeah, so if it said evaluate this, that kind of makes sense, doesn't it? All I'm doing is just putting that in there and there. Now I'm gonna do that, and then at the end, I'm gonna find out what the real part of my imaginary number, sorry, my complex number that I end up with is. Okay, so let's just keep going. So it's going to be 9. I'm going to do this kind of quickly. 6i, yep, plus I squared minus 3i plus I squared. Okay, so I've got 9s there. This and this is going to make minus 9i plus I squared, that's plus 2i squared. Now keep in mind that I squared is equal to minus 1. So then 9 minus 9i plus 2 outside of minus 1. So it's going to be 9 minus 9i minus 2. So that's going to be 7 minus 9i. Okay, is that correct? Yes, it is. Okay, so then if I want to find the real part of what I just worked out, then that's just literally the 7. So that's the real part, and that's the imaginary part. So the real part is 7. That's it. So I think that's just kind of like a standard question. You know, that might be a 1 marker, but it doesn't look easy just kind of because it's all this new stuff that we don't really use Zs and RE and stuff like that. But at the end of the day, it's not actually that bad. Okay, that's all I want to talk about in real and imaginary parts. Now let's talk about adding, subtracting, timesing, and dividing. So if I want to add two complex numbers, you just add each of the, if you want to add anything, you just write them as if you want to add them. So I'll use the same Z1 and Z2 as before. If I want to do Z1 plus Z2, then that's just A plus BI plus C plus DI. And then you can just kind of go from there. So if I just expand that, there's an A plus C there. Actually, let's leave that. And there's a BI plus a DI. So, you know, the real component will be A plus C, and the imaginary component will be B plus D, and you know, just work like that. And so then if I do take away, same thing, Z1 minus Z2, just write them in brackets, A plus BI minus C plus DI. Okay, so then that just becomes A minus C and B minus DI. So really, if you're just adding two complex numbers, just add up their real and imaginary components, and then you should be fine. If we're timesing, so if I've got Z1 times Z2, I'll move that up, consistent. Okay, same thing, A plus BI, C plus DI, and for something like this, you probably just need to use FOIL, but you know, I guess I'll do that. AC plus, okay, so AC, and then make that, so I'm going to have room to do the next one. A DI plus BCI plus BI DI BD AC plus ADI plus BCI, and then we've got an I squared here, so this is basically just minus BD. And I could simplify. I could get the real and imaginary parts next to each other, but who really cares? The next thing I might want to do is square a complex number. So if I've got Z1, I'm trying to square it, and that's just A plus BI squared. And if you just use your perfect square expansion, like the quick version, or if you just write them next to each other, it doesn't really matter. I've got A squared plus 2A BI plus BI squared. always remember that I squared can be simplified. So if you ever have a power of I, don't ever leave it like that. Just write it as minus b. Okay. Oh, squared. B squared. Oh, I almost stuffed it. B squared. Okay, so let's do an example. So I've got, let's go, given a numerical example. Given P, I'm going to call them P this time, minus 2 plus 3i, and Q. I think Q are pretty common to use for examples like this, especially in extension. Okay, P plus Q. So that's just minus 2 plus 3i plus 1 plus 2i. So that's going to be minus 1 plus 5i. I want to take them away, be a little bit more careful with your use of brackets. I wasn't there because, it was addition, don't really care, but you just got to be careful with this very end term, especially when there's a minus here. So I'm going to have minus 3 and plus I. Do I do another one? Yeah, PQ. Let's do that, eh? So that's going to be minus 2 plus 3i, 1 plus 2i. Okay, FOIL. FOIL. Minus 2 minus 4i. Oh, already did that. Plus 3i plus 6i squared. Minus 2 minus I minus 6 minus 8 minus I. So remember, that can always be simplified to minus 1. Okay, so one thing I want to further look at is something called the conjugate. So I believe this was touched on in our little intro lesson before, but it does have a little bit of significance. So when we're multiplying and you see a conjugate times by itself, so the example we had on the other page was 2 plus or minus 3i, so 2 plus 3i, 2 minus 3i. What you're going to find is something kind of interesting, and it's this. Let me just expand it. I'm going to have 4 minus... It does seem childish that I'm using FOIL because this is genuinely how I work things out. Plus, minus... Whoa, minus 9 squared. 4. What you'll notice is this. The imaginary parts always cancel. And we're left with an I squared here, which will give me this, which will give me 13. Okay, so what happens is whenever you multiply the conjugates together, what you actually end up with is not a complex number, any number's a complex number, but you end up with a complex number that does not have an imaginary component. So it does not have an imaginary component, and this is really, really helpful. So if I do this in general, so if I have a plus bi, and I have a minus bi, what I'm left with is a squared plus BIA minus BIA. I probably shouldn't write it like that, it looks weird. Minus B squared I squared, which equals A squared plus B squared. Is that right? That seems right to me. Okay, so whenever you multiply the two conjugates together, what you actually end up with is the real and imaginary parts squared and added together. And that's a really important result because, and I guess you can think of it like, when do you use the conjugate? So I'm not going to cover it right now. I'm going to cover it towards the end. But you have seen the word conjugate before. Just try and think about where you might have seen it before. And I'll talk about why this result is important in a sec. Okay. Oh, also one thing. If I've got z, whoops. So if z is equal to a plus bi, then the conjugate z bar, so z bar represents the conjugate, is a minus bi. Okay. And if you take the conjugate twice, you end up with what you started with. So also z bar bar. So if I take two conjugates, I end up with what I started with. Okay, so that's what the conjugate is. Next thing I want to look at is division, because that's what I haven't really covered yet. So I've covered plus, minus, times, squaring, timesing conjugates. Now let's look at division. So there is a slight problem with division, and it's this. Let's use the P and the Q example. So if I do P divided by Q, so that was, what was P and Q? Minus 2 plus 3i and 1 plus 2i. Okay, if I try and do this, my problem is I can't, like, there's nothing I can do. Like, I can't factorize the top line and cancel things. I can't just go, see you later. Like, I can't take a common factor out. I'm not even sure if this is something I'm allowed to do. Like, complex numbers is a new thing. I don't know if this is, like, illegal or anything like that. So there's actually nothing I can do to simplify this. So cannot simplify. So this is something I can't touch at the moment. But what I can do is something called realizing the denominator. And this is something you've seen before, but we've seen rationalizing the denominator. So what you'll notice is when you're looking at stuff like, I don't know, like 1 plus x, and then you've got like the square root of 1 plus x or something like that. Maybe that's a little bit easy, something like that. It's kind of hard to do anything. Like there's not much you can do with this, right? But what you would have learned is to rationalize the denominator, which meant, okay, I'll times by square root, and I'll, instead of having 1 plus x, I'll do 1 minus. And then what ends up happening is the square roots actually cancel, and what you're left with on the denominator is a real thing, sorry, a rational thing, which means it just doesn't have a square root on it. So something like 1 on root 2, you'd actually 1 on root 2 plus a, you'd multiply that by 2 minus a and 2 minus a, and you'll find that these disappear, the square roots. Is that true? No, it's, sorry, it's square root of 3 plus something, I believe. God, I haven't rationalized the denominator in a while. It's something like that, and then you have a minus, and you'll notice that because you have to times this by itself, the square root disappears. Actually, I haven't rationalized the denominator in ages. Anyway, so it's the same thing with realizing the denominator. All you're doing is making the denominator real. So in this case, if I'm left with a denominator that has a 1 plus 2i on it, if I were to times that by its conjugate, then the solution, or the denominator, is going to become something that's real, which is what actually happened in this this expression here. So what I can do with my division problem, so minus 2 plus 3i, 1 plus 2i, okay, is if I times that by 1 minus 2i and 1 minus 2i, what's going to happen is, okay, the top will not look that great. Plus 3i, 1 minus 2i, actually it might, okay, but the bottom is going to look really great. So recall from up here that when I multiply these two conjugates, I end up with this squared times this squared, which is the same thing as what's going to happen here. If you're not confident in that, obviously just sit there and expand it, but I'm just going to end up with this squared plus this squared. So 1 squared plus 2 squared. And when you rationalize the denominator, you end up with a difference of 2 squares. So it's the same thing, except you end up with a minus here. So all this stuff kind of links together, which is pretty cool. All right, so on the bottom here, I've got 5. And on the top here, I'm going to have minus 2 plus 4i plus 3i minus 6i squared. Okay, then that's going to give me, what have I got? I've got minus 2 plus 7i plus 6 on 5. That's going to be 4 plus 7i on 5. And you can write that. It's also unknown whether this is a property that you can kind of leave it as. Like, is this a complex number? Because before we were saying that complex numbers have to have strictly real and imaginary parts. This doesn't. This is just a fraction that has a complex number on it. So it's kind of important to ensure that your final answer is kind of written like this: 4 on 5 plus 7i. 5, something like that, so that you know that 4 on 5 is the real part, 7 on 5 is the imaginary part, so that's made really obvious to the reader. And I guess that's kind of all I want to talk about. Let's do some examples. Okay, let's do examples with the conjugate, because that's kind of interesting. Let's not use P and Q again. I'm going to use Z. Let's do 3 plus 4i. Okay, so what I want to find is Z plus its conjugate. So that's going to be z plus its conjugate, so 3 minus 4i. Okay, so the 3's, right, and then I guess these just cancel out. So 4i minus 4i, nothing. So we just end up with 6. If I then go with a subtraction, got 3 plus 4i, minus 3 minus 4i. What you end up with is, you'll see that these will just cancel, and I'm going to end up with a plus here, so you just add the two imaginary parts, and I end up with 8i. So that's kind of cool. When I add two conjugates, I end up adding the real parts. When I subtract two conjugates, I didn't even write conjugate on there. When I subtract two conjugates, I end up with a sum of just the imaginary parts. So, yeah, I think that's kind of interesting. I guess what you could also say is this just equals the sum of the imaginary parts. So you could write the imaginary part of z plus the imaginary part of z bar. That's kind of interesting. That's one way you could write that. Similarly, you could write this as the sum of the real parts. So the real part of z plus the real part of z bar. Anyway, why did I do that? God knows. Okay, I know what happens when I multiply two of them, so let's not do that, it's kind of boring. Let's divide, so z divided by z bar, or z conjugate. 3 plus 4i, 3 minus 4i. What do I need to do? Can't touch that, so I'll times by the conjugate of the bottom. I'll realize the denominator. Realize that it's not actually that hard. Okay, so this ends up being 3 plus 4i squared, and this ends up being 3 squared plus 4 squared. Okay, 3 squared plus 4 squared. Oh, that looks like a 3, 4, 5 triangle to me. That's 25. This thing is going to be 9 plus 3 times 4 is 12, 24i. That's right, isn't it? Plus 16i squared. Okay, that's equal to, that's going to be minus 16. So 9, so I'm looking at this, 9 minus 16. Minus 7. Minus 7 on 25. Plus 24 on 25i. Alright, I think I've rambled long enough. That's a long video, 27 minutes. But yeah, this is all the stuff we can do with complex numbers. So before we looked at all the things we could do with just the imaginary part, now we've just looked at all the things we can do with the full complex number, so the full z, including the imaginary part. Okay, so that's it for today. And I'll actually see you guys next week, so that's kind of exciting.